Welcome to Algebra. Finding roots of a polynomial can feel like searching for a single suspect in a massive, crowded city without any clues. If you have to guess blindly, it is practically impossible. But mathematicians have discovered incredible shortcuts that act like a detective's filter, narrowing down infinite possibilities to just a handful of highly likely suspects. Today, we will explore three of these powerful shortcuts: the rules governing imaginary, integral, and rational roots. Let us dive in and save you countless hours of blind guessing. Now that we understand our goal, let us begin with the fascinating behavior of imaginary roots. In the real world, certain things only ever come in pairs, like shoes or gloves. A very similar rule applies in algebra. The complex conjugate root theorem states that if a polynomial has only real numbers as its coefficients, any imaginary root must have a partner. If a plus bi is a root, then a minus bi must also be a root. These pairs are called complex conjugates. They are mirror images where the imaginary part flips its sign. They must appear together so their imaginary parts cancel out during multiplication. This concept leads us to the mathematical setup for multiplying these conjugate pairs. When we know a polynomial has an imaginary root, we write its factors by subtracting each root from the variable x. Here, x represents a variable. The letters a and b represent real numbers, forming the real and imaginary parts of our root. Finally, I is the imaginary unit, the square root of -1. If the value of b increases, the imaginary part grows larger. But because we multiply the conjugate pair together, the imaginary components will always perfectly cancel out, leaving us with strictly real coefficients. Before we prove why this always works, let us see this with a concrete example. Suppose you are asked to find the lowest degree polynomial with real coefficients that has 3 plus 4i as one of its roots. We are only given one root, but our theorem tells us the conjugate 3 minus 4i must also be a root. We set up our equation by writing x minus each root. To make the multiplication simpler, we group the real parts, x and 3, together in both factors. This cleverly sets up a classic difference of squares pattern. Continuing with our multiplication, we apply the difference of squares rule. We square the first group, x minus 3, and subtract the square of the second group, 4i. Expanding the first group gives x squared minus 6x plus 9. Squaring 4i gives 16i squared. Since I squared is -1, subtracting -16 becomes adding +16. Combining the constants 9 and 16 gives our final polynomial, x squared minus 6x plus 25. Physically, this represents a parabola that never crosses the x-axis, which is exactly why its roots are purely imaginary. Now that we have used this rule successfully, let us understand where it comes from by looking at the formal mathematical derivation. We want to prove that multiplying any imaginary root by its complex conjugate always results in strictly real coefficients. We start with the general factors, x minus the quantity a plus bi and x minus the quantity a minus bi. Just like we did in our concrete example, we rearrange the terms inside the parentheses by grouping the real parts, x minus a, together. This strategic grouping allows us to apply the difference of squares formula, resulting in the first term squared minus the second term squared. Continuing our derivation, we expand the squared binomial x minus a to get x squared minus 2ax plus a squared. Next, we square the second term, bi, which gives b squared times I squared. Because I is defined as the square root of -1, squaring it gives exactly -1. The double negative turns into a positive sign. Look closely at this final result. Every single piece of this expression is a real number. The imaginary unit has completely vanished. This proves that pairing an imaginary root with its complex conjugate guarantees the polynomial will have strictly real coefficients. So we have proven how imaginary roots behave. This brings us to whole numbers, specifically the integral root theorem. Think about trying to pack 12 apples into boxes so that every box has the exact same number of apples with none left over. You could use boxes of 2 or 3, but never 5, because 12 divided by 5 leaves a messy remainder. The integral root theorem works on this exact same logic. It states that if a polynomial has integer coefficients and a leading coefficient of exactly 1, any integer root must perfectly divide the constant term at the very end of the equation. To see how this works, we write out the general form of a polynomial equation. Here, k represents our assumed integer root. The letter n is the highest power or degree of the polynomial. The various c values are the integer coefficients, and c0 is the constant term at the end, which has no variable attached. If the constant term c0 increases in size, it gains more factors, which physically means there are more potential integer roots to check. This formula sets the stage for finding those exact whole number solutions without guessing blindly. Before we prove this theorem, let us solve a problem using it. We need to find all the integer roots of the polynomial equation x cubed minus 4x squared plus x plus 6 equals 0. Instead of guessing random numbers like 100 or -42, we use our theorem to create a short list of suspects. Our strategy is to first identify the constant term, which here is 6. Then we list all the integers, both positive and negative, that divide evenly into 6. These factors are plus or minus 1, 2, 3, and 6. Now that we have narrowed down infinity to just 8 possible numbers, let us test -1. We substitute -1 wherever we see an x in the original polynomial. Calculating the powers first, -1 cubed is -1 and -1 squared is +1. Performing the basic addition and subtraction from left to right, we get -1 minus 4 minus 1 plus 6, which equals exactly 0. Because the result is 0, we have successfully found a root. Physically, this means the graph of our polynomial crosses the x-axis exactly at the coordinate -1. Now that we have successfully found an integer root using this method, let us prove why this theorem must always be true. We start with our general polynomial equation, where the leading coefficient is exactly 1, and all other coefficients are integers. We assume that there is some integer k that is a valid root, which means plugging k in for x makes the entire expression equal 0. Our mathematical goal here is to show a direct relationship between the root k and the constant term c0. To do this, we isolate the constant by moving c0 to the right side of the equal sign by subtracting it. Continuing our proof, notice that on the left side of the equation, every single term contains at least one k. Because k is a common factor to all terms on the left, we can factor it out to the front. Look closely at the expression inside the parentheses. It is made entirely of integers being multiplied and added together. When you add and multiply integers, the result is always another integer. Let us call that entire massive integer m. This simplifies our equation significantly to k times m equals -c0. This final equation is the exact mathematical definition of divisibility. It proves that any integer root k must perfectly divide the constant term. So we have proven the rule for whole numbers. But what happens if the leading coefficient is not an invisible one? This brings us to the rational root theorem, the ultimate upgrade. A rational number is simply any number written as a fraction. This theorem states that if a polynomial has integer coefficients, Any rational root must be a fraction where the top number is a factor of the constant term and the bottom number is a factor of the leading coefficient. Think of it like a recipe where the total yield is controlled by the top and the base size is controlled by the bottom. This concept gives us a new formula to work with. We assume our polynomial has a rational root in the form of a fraction, p over q. Here, p represents a factor of the constant term a0 and q represents a factor of the leading coefficient an. We also assume p and q are coprime, meaning the fraction is fully simplified. If the leading coefficient an increases, it generates more factors for q, which physically means the polynomial could have more fractional roots tightly packed together. We substitute this fraction into the polynomial for x. Before we calculate anything, let us visualize how this theorem builds our list of suspects. In this diagram, you can see the general polynomial equation at the top. The red arrow shows how the leading coefficient an drops down to provide the factors for our denominator, q. The blue arrow shows how the constant term, a0, drops down to provide the factors for our numerator, p. By combining every possible p with every possible q, we construct the complete master list of possible rational roots. This visual map shows exactly where every piece of our fraction comes from. Now that we have visualized the formula, let us see this in action with a final example. We need to find all possible rational roots for the polynomial 2x cubed plus 3x squared minus 8x plus 3 equals 0. Because the leading coefficient is a 2 and not a 1, we must use the full rational root theorem. Our strategy is to identify the constant term, which is 3, and list its factors for our numerators, p. These factors are plus or minus 1 and 3. Continuing with our setup, we next look at the leading coefficient, which is 2. We list its factors for our denominators, q, which are plus or minus 1 and 2. Now we build our fractions by taking every possible value of p and dividing it by every possible value of q. Dividing by 1 gives us the integers plus or minus 1 and 3. Dividing by 2 gives us the fractions plus or minus 1 half and 3 halves. We have successfully generated a master list of exactly 8 possible rational roots to test. From our generated list of 8 possible rational roots, let us test the simplest one, positive one. We substitute 1 into the original polynomial. Since 1 to any power is just 1, the calculation becomes very simple. We just multiply the coefficients by 1, giving us 2 plus 3 minus 8 plus 3. Adding and subtracting from left to right, 2 plus 3 is 5, minus 8 is negative 3, plus 3 is exactly 0. Because the result is 0, 1 is indeed a rational root. Physically, this confirms the graph intersects the x-axis at exactly positive 1. Now that we have used this powerful theorem to find a root, let us understand exactly why it works by proving it mathematically. We start with our general polynomial equation and substitute our fully simplified rational root, p over q, in place of x. Fractions make equations very difficult to work with, so our first logical step is to clear them out completely. We do this by multiplying every single term in the entire equation by q to the power of n, which is the highest power of the denominator present. This clever algebraic move cancels out all the fractions, leaving us with a clean, flat equation made entirely of integers. Continuing our proof, we want to show that p divides the constant term a0. We move the very last term, a0 times q to the power n, to the right side by subtracting it. Look closely at the left side. Every single term contains at least one p. We factor this common p out to the front. This equation tells us that p multiplied by some large integer equals negative a0 times q to the power of n. Since p and q share no common factors, p cannot divide q. Therefore, the only mathematical possibility left is that p must divide a0. This perfectly proves the rational root theorem. We have covered a lot of ground today, so let us review our key takeaways. These three rules are the ultimate tools for breaking down complex polynomials. First, the complex conjugate root theorem ensures that imaginary roots always travel in pairs, keeping our equations grounded in real numbers. Second, the integral and rational root theorems act as powerful filters, turning an infinite guessing game into a small, manageable checklist by simply looking at the first and last numbers of the equation. You now have the exact tools needed to start solving higher degree polynomials with confidence.